Okay, Chapter 6, Procedures. Now, we have just started dealing with mixed mode programming. In Chapter 6, we will continue that, where we're going to use all of the benefits of a high-level language, readability, writing, editing, all of that. We will harness those efficiencies where we can and only write things in assembly where we know we can do them a little bit more efficiently than the high-level language can. Now, I say that's the way we would do this in theory. But what we're going to do for the class is we may use some examples where what I show you is absolutely not an efficient way to do things. However, it is sufficiently simple that it's easy to understand the mechanism, so that when you have something you know is more efficient, which we're getting there, but then you will know how to implement this. So in Chapter 6, in the book doesn't deal with mixed mode code. So what we're going to do is we'll introduce stacks and pushing and popping on the stack. Then we'll deviate from the book and go look at mixed mode programming, or specifically what are the calling conventions for C++. And then we'll come back to Chapter 6 and pick up the other things that we might need that I think you might see, if you ever look at this stuff again. So that's how we're going to proceed for Chapter 6. So first, let's talk about the data structure stack. You guys are familiar with this. A stack is a linear list of data that's accessible at only one end. That end is called the top. Usually, one of the stereotypical examples for a stack is a roll of coins. So let's say I've got a roll of coins, and I want to load my roll of coins with nickels. So let's say I've got a nickel, and I want to put it on the stack. So what I'm going to do is I'm going to take my nickel and push it onto the stack. Okay, so let's say I push 1, 2, 3, 4 nickels on the stack. And let's say I forget that the third nickel, this one right here, is actually a buffalo head nickel. And I want to keep that one because it's worth a little bit more than 5 cents. What I have to do, though, is remember we said that it's only accessible, the data is only accessible from one end called the top. Well, this is the top right here. The fourth nickel is my top. So what I've got to do is pop that nickel off before I can get to my buffalo head nickel. Okay? So because of that, it is a last in, first out structure. Okay? In high-level languages, you'll frequently see a stack implemented as an array, although it's certainly not limited to that implementation. Now, when we think about a stack, we will not be limited to the definition of a stack that you've learned in data structures or that you've learned so far in your intro sequence. We need to understand how it works, but then we're always working at a little bit lower level, so we've got a little bit more advantage. We're not limited, but we will use that model to help us. So there are 2 different models for implementing a stack. On the left, I have a stack that grows toward high memory, okay? So from low to high. On the right, I've got a stack that grows toward lower, so it goes from high to low memory, okay? And it turns out, in most computer systems, the second model is the most convenient for implementing stacks, and we'll talk about why as we start talking about the instructions that we have. But before we get to that, let's go back. Remember when we were dealing with all assembly language programs, we had the stack directive, and the stack directive was our way of allocating 4,096 bytes, in this case, to a runtime stack. But how does this work? Well, let's take a look at it. Okay, so when I allocate a 4096 byte piece of memory called the runtime stack. What it's going to do is it's going to allocate that memory. So it's going to take whatever the stack pointer was pointing at, move it 4096 bytes past, and so there's the 4096th byte right there. It's going to move the stack pointer and put the address of the byte just beyond the top of the stack in ESP. So ESP is pointing just beyond the top of the stack. That's okay because that's going to help us with our implementation model. Okay, so the next question is then, how do we use the stack? Well, we're going to use it the same way you would think, the way we talked about when we talked about our roll of coins. We're going to push words or double words and occasionally a byte on the stack, and we will pop them off when we need them. So you say, okay, well that tells me how we use it, but is there an instruction? And yes, there is, absolutely. Okay, here is, whoops, I went too far. Here's the push routine, okay? As I mentioned, most of the time, my operand, the source, is going to be a word or double word. The only byte-size operand is an immediate value that's going to be allowed. Sometimes, when you're dealing with immediate values, you can use push W or push D to explicitly indicate the size of the push. Okay, so let me tell you what this thing is going to do. Push is very similar to the loop instruction, where it's actually a complex instruction, not an atomic instruction. This is going to do a couple of things. So first, okay, it's going to decrement the stack pointer by the size of the push. So in this case, by 2 or 4. And then it will copy source to the stack. Okay? And hang on, I'm going to give you, we'll draw some examples in just a second. Pop does the opposite. Whoops, went too far again, sorry. Pop does the opposite of push. The destination in this case can reference a word or double word in registers or memory. Even segment registers can be the destination. But it cannot be an immediate value, for the same reason that our destination operand in other instructions cannot be an immediate value. The destination has to be a place that can store something. Okay? So, what this is going to do is it's going to copy the word or double word. Ooh. Copy what ESP is pointing at. So we'll say top of stack to destination. And then it will post increment the stack pointer. Okay, so again, it is a complex instruction that does a couple of things at once. So let's look at an example. So for this example, I've actually got all assembly language again, and here what we're going to do is we're going to look at this example. We allocate a stack. So let's say our stack looks something like this. And we'll draw this for now without indicating exactly what it's going to look like in memory. We'll come back and do that in a second. Let's just kind of do this. So stack pointer is right here. Okay, I've allocated my stack, so that instruction is done. I get here to push the double word 25 on the stack. I pre-decrement my stack pointer, push 25 on the stack. Okay, and now my stack pointer is pointing at the top of the stack, or the byte just beyond the top. And then I'm going to push another double word with an initial value of 10 on the stack. So again, I'll pre-decrement, push a 10 on the stack, and there I am. So right now, stack pointer is pointing right here, not here anymore. And now I'm going to pop whatever the stack pointer is pointing at into EAX. So I'm going to copy this double word value into EAX. EAX, as a result, will be 00000000A, and then I will increment, the stack. So let's show that. So we've copied this into EAX, and then we post increment, the stack. So at the end, I know this is a mess. Stack pointer's pointing here. It's no longer pointing there. Okay, at the end of this. All right, well, let's see if we can clear this up a little bit. We'll do the same thing, but this time we'll look at what it's going to look like in memory, actually. Hopefully, if we can get there.